GPDK.
Array,
why this many? Only one is required, no? One is enough, right? This many is not required. One you can keep.
एकदम उठो.
Okay. Your wish. It seems like. So you have here RF, LO, I'm naming like RF LO IF. I'm keeping analog lib. You place GPDK resistor. This part is not required. No, only simulations part is required. You keep with the 50 ohm port only for simulations. Okay. Frequency, let's say. PAC magnitude you keep 1.
So you should give value of that.
Where? I'm taking a variable. This is the name of it. I'm taking a variable. Here, when you are giving multiple, you can give pulse width here, but I'm not giving, so 50% I'm taking. Just to show simulations, I'm taking this. Let's say this simple switch and some resistor was there. A given RF with some frequency FRF frequency with amplitude P in. And LO 0 to VDD it is switching with time period TP. Okay, what are the values and all we'll see. Okay, so when you launch ADL,
So can you once display the port?
this frequency and P in we need to, and PA small signal parameters to enable. This one during PAC analysis you did, right? PAC magnitude in place of this one also you gave variable. Present I gave one. When we do IAPT simulations, we'll give it here also variable. So that we need to do separately. So when we are doing that, we'll change. Or else we can do here also, but we need to verify. But I don't want to confuse. This is I just I gave name. To say let's say at 0.9 gigahertz we are doing simulations. In is let's say I'm giving something like minus 40 dB. Time period 900 megahertz. Same as FRF I'm taking. 1 EDD 1.8. Okay. So while doing this one, this DC AC noise, DC simulations are same. AC noise, XF, SP, these simulations we did. Instead of that, now we need to do PSS with PAC, P noise, PSP, PXF, these kind of simulations, and QPSS and QPS. So select PSS. It will come here default the name these tones, but here the names it is not for port we gave the name FRF1 as the name. If you see here we gave the frequency name. What is the frequency name we gave, and this is the frequency, actual frequency. Okay, but when you see the LO also to be with the port, but since we are not dealing with the matching and all, for this one we are not doing the port. So LO also here frequency name for 1 by period is there. This we didn't give, but please mention this name also, because when you do IIT simulations it will throw an error. So give the names. Okay, so these are the showing the names. These two are there in the fundamental tones. One is FRF, another is this one. Both are 900 MHz large, and these are the source V0 and port. Okay, this beat frequency same as like in PSS, PSC how you give, here also you can give.
Had to calculate.
Either you do auto calculate, since we are not doing with any harmonic those things, and you can do auto calculate. This number of harmonics maybe you can mention 7 is enough for this.
7 harmonics.
Don't sweep and anything.
Conservative.
It's okay to keep. But when you do in the linear, I mean LNA linearity checking, you did sweep and you verified, right? So for this one we don't do. This is not related to linearity. So just we are doing periodic steady state analysis. So now to do PAC, AC simulation of this circuit, you select the PAC. So input frequency sweep range. For what frequency sweep range you wanted to verify your circuit. So let's say you wanted to check from the 900 MHz to 800 MHz to 1 GHz. So with maybe you can mention 800 MHz to 1 GHz here, or you can mention center span, saying that my center is at 900 MHz, and either side it is expanding 100 MHz. Means total span is 200 MHz. So it is like 800 MHz to 1 GHz it will go. So either, since we are from FLO, we are seeing both the sides. So you can either select center span or start and stop, you can give both. And here sweep type, all these frequencies it will analyze. So let's say 1 MHz sweep, I will take each 1 MHz frequency. And maximum sidebands, even if you don't mention, it will take 7. Even if you mention also, it's fine. So apply. So when you do PSS PAC, it will give the conversion gain analysis. So and we'll see PXF also. What PXF will also do. When you do PAC, it is asking input frequency sweep range. Okay. When you are doing PXF, it is asking output frequency sweep range, where your output lies. So according to that, it will back calculate. So let's say your output is also now centering at 0. Let's say I'll keep it as, instead of 0, it will not take 1 to 200 MHz. Means your output is this 800 to 1 GHz, whatever is there, this is converting to direct down conversion you are doing, that 900 MHz. So this my output is like this one. So according to that, it will back calculate its inputs. So this also I'll do same like 1 MHz. Maximum sidebands default I'll keep it 7. But here we are asking positive output node. What is the positive output node? What is the negative output node? Since we have only one positive output node, I am selecting this one. And if you have differential, you can select differential here. But since we have ground, I am selecting the ground here. Voltage, it's fine. There are certain options. When you go into options, there are this kind of frequency axis and all. We'll see. Wait, that I'll come back again. So in the PAC also there are certain options. These are where this axis and all will come. We'll see when after doing the simulations, based on the results how we are getting, we'll see. So same, instead of same PSC, PXF, P noise also. Output frequency sweep range it is asking. So what is my output frequency? Let's say this is also I'm taking from 1 to 100 MHz. This side. One side is 100 MHz, other side is also 100 MHz. Either or center span you can keep, and you can do this way. Okay, both the sides it will take 100 and 100. So linear, and keep taking 1 megahertz. This is step size. Every 1 megahertz it will analyze.
No, that's
Yes.
center.
This is center, means instead of 0 I'm taking 1. 0 it can't handle. From 0 onwards it will, from 0, from 0 it will be 0 IF, right? FRF and FL both are at same frequencies. If it is different frequencies, according to that you need to PSS beat frequencies. Here you gave this beat frequencies this one because these two are same. When you are doing high IF down conversions, these two frequencies will be different. Obviously your beat frequency will also change, right? So what I'm doing, noise. So P noise. So if you want to calculate, select noise figure. Output, since we are taking voltage, select the voltage and select the positive output node. Same. Negative output is ground. Select the ground. I mean, here it's the ground one. And the input source. This is a port. So select the port. So this port comes here. Enter in the field reference. Maybe here it's not showing reference sideband. Like at what sideband you wanted to see. If you know directly, you can enter the number. If you are not sure, go to the select from the list. Here it will ask maximum order. It will give 1, 2, 3, 4. At what harmonic you wanted to see. Since our input is at 800 to 1 gigahertz, you can select upper or lower. Mostly you will select upper band. You can say this is upper side or lower side. You can see upper. You can select upper, no problem. 800 to 1 gigahertz and this one. If you know this number directly, you can directly enter here 1. Okay. Or else you can drop down, select from list, and you can select here. It will automatically select. Okay. You select upper, this one USB, upper side band. So apply. So this PAP, these all analysis are now adding, right? So what else? Let's say PSP also we wanted to do. PSP is the S parameter simulation. Same here also, frequency sweep range. From where to where you wanted to sweep. Or you can center span also. Let's say this one is also I wanted to sweep input frequency 900 megahertz to 900 megahertz, and both the sides I want to keep 100 megahertz and 900 megahertz. And sweep type linear I'll keep 1 megahertz. And at what port you wanted to do the S parameter analysis. You can select the port. Let's say RF port I wanted to see the S parameters. Not required for this, since we are considering this mixer will come after the LNA. But for suppose if you wanted to do mixer alone, or mixer, at some cases mixer you wanted to impedance matching and all, then you have to do this S parameters and all. So give the port. This is a 1 means it will consider as port 1, S11, Z11 like this. If you give 2, it will come 1, 2 with respect to 2. And choose the harmonic. So here also select your input 800 megahertz to 1 gigahertz. Your input 0, 1. So and then add, it will come here. Okay. So if it comes this one, it will analyze. If you want to do another port, if another port is also there in the schematic, you can select the select port, and that port, selecting that port, you can do there also as parameter analysis. Do noise, maybe you can click no for this. From this also you can do noise analysis, but since we are doing with the P noise, you click no. Okay. Now if you see here, along with the for conversion gain, we added PAC and PXF also. We'll see what kind of results will come, and the P noise and PSP. Okay. Now let's say we'll do run the simulation. Maybe you're not doing IIP3, we'll see. Okay, now the simulation is run, right? So go to results, direct plot, main form. In the main form, if you see PSS, all these kind of things came. PAC, voltage gain, these things there. P noise, noise figure, NFDSB, noise factor, output input noise, PXF also voltage gain, transimpedance, PSP, this S parameters, Z parameters, all this. Same things which you did for AC simulation, noise figure noise simulations. This kind of results only will be there. But with respect to periodic circuits. Okay. Now if you go to the PAC, let's say I wanted to see the voltage gain. You have only output and input nodes. Select output and input nodes. If you have differential, select output plus minus or input plus minus. So if you want to see the complete spectrum or sideband, if you put the sideband, it will ask input sideband to the output sideband. If you put the full spectrum, it will give the, if you did PAC analysis for 7 sidebands, right? all those 7, it will give the spectrum. If you want it to specific to 1, you can select the spectrum. In dB20, you can select what is the input harmonic. Your input is at 800 megahertz to 1 gigahertz. So now it is asking select the numerator output net on the schematic. So this is my numerator output. I selected, and then it's asking select a denominator input net on the schematic. So this is the RF is my denominator input. I'm selecting RF. So what it is giving, these are all different gains, different sidebands it came, right? So let's say 0th one, it came around here, right? 800 megahertz to 1 gigahertz. This is my conversion gain. What is the conversion gain? Minus 8.24 dB. Means this is a lossy circuit. This conversion gain is minus 8 dB. Okay. So this is not only for this harmonic it will work, because our LO is having all the harmonics. FLO is there, 3FLO, 5FLO, all these harmonics are there. So if you see the next one, minus 1, with respect to minus 1 or plus 1, where it is they are down converting. With if means this is the, with respect to fundamental, this came to 0. This is from second harmonic, means 2FLO if it's down converts it comes here. 3FLO if it down converts it will come to the second one, like that. Second, third, these all different harmonics exist. These are all different harmonics where they are present. Okay. So
what is the numerator and denominator?
numerator is output, denominator is input, right? AC analysis. So this is the your conversion gain represents. Okay. This is at with respect to FRF, it's shown with respect to FRF scale. All these harmonics, maybe it's not highlighted. No? So all with respect to all the harmonics, it's shown where all the down conversions exist. Okay. What else? Next, let's say with respect with PXF also we did some same simulation, right? Let's say with PXF, I'll take new window or maybe new sub window. I'll take. So voltage gain dB20. This also I'm taking a spectrum. Since already we gave when we are doing PXF analysis, we gave here what are the output and this one. So it is asking with respect to which port or voltage source you wanted to do the schematic. Select that port. So since this port we wanted to do the analysis, select this port. It came with respect to output. So if you see this output, this one is coming minus 2.39 dB. Why this result different? This is the zero down conversion, right? With respect to output, it is means after FRF minus FLO, this one, and these are all remaining down conversions. Okay, this is the with respect to output scale. This is with respect to input scale. This PAC gave with respect to input scale. This gave with respect to output scale. But if you see this conversion gain, you get minus 2.39 dB. This one you are getting minus 8.244 dB. Any why? Anything why it is coming different? When you are doing PAC analysis, you are specifically taking this is the output, this is the input. But when you are taking the port of the circuit, it is like earlier first to the first experiment. I think when you are doing practicing, you are getting that 6 dB difference because your voltage source and resistor is there. So but here you are selecting the port with respect to port inside that what it's giving, based on that it will check. Okay. So if you wanted to see with respect to output axis what it is coming, you can see this one. But if you want exactly see PAC analysis is more clear. You can select okay this port to this node to this node, I'm getting this much conversion gain. So that is exactly clear. But if you want to see with respect to output scale, then you can do PXF analysis also. But mostly we will go PAC. It will be clear. You can select nets. Okay, this to this much gain. Okay, anywhere you can select those nets, so those conversion gains will come. So better you go with PAC. PXF is also will be helpful sometimes. But when you are clear about what you are doing, do that analysis. Okay. So if you see this PXF, These are all come with respect to the output. This down conversion. These are PAC. These down conversions are showing with respect to the input frequency scale. Okay. Now, what are the other things we did? P noise analysis. P noise, maybe output noise, input noise, noise figure, NFDSB. What is this NFDSB noise figure? Are when you are down converting, when you are specifically down converting to zero, your spectrum is lying both the sides. That is DSB means dual sideband, both the sides of upper sideband, lower sideband. So it will exist both the side. When you are doing IF down conversion, it will be on the completely in your positive frequencies or wherever frequency you want to see. So when you see this noise figure noise figure, this is a single sideband noise. This completely one side spectrum you will see. NFDSB is like two sided spectrum you see. So it will be like half of the noise it will come. We'll see. If you see, we'll understand. So now NFDSB already we gave in the noise analysis what is the output, what is the port, and at what is the input harmonic. So let's plot. So this is the noise figure I got. At 1H, since because of flicker noise, it is very high, it is coming. And other frequencies, it is coming now. My noise is 20.66 dB. For this circuit, the noise is 20.66 dB. So this circuit will work as an mixer. The circuit is also showing down conversions, but it is having some loss, conversion gain loss. Conversion gain we call, but it is a loss. And it is having noise figure of 20 dB. So that is its property. So if you place capacitor, what will happen also you see. Okay. So if you see the noise figure on the, I'll append it. If I plot, it will be shifted by 3 dB because of single sideband. When you take double sideband, it will become half of it. It will spread both the sides. Since it's zero IF down conversion, it will become dual sideband one. When you are taking IF down conversions, if when you see, like for suppose you are designing a mixer for heterodyne receiver, there your IF lies at some frequencies, right? So that time you will get single sideband spectrum, all the noise will be there. So that time you have to see the noise figure. When you are doing for zero IFs, it will exist in both the sides, so you will see NFDSB. So because of this, both the sides, the noise spectrum will get difference of 3 dB. So for 0F, you please select the NFDSB and do the check the result. And another is PSP. It is same like S parameter simulation. SP. You can select. Let's say S11. If you plot, let's say new window. I take S11. So something like -3. That means almost 0 dB. Means all it is reflecting. It is having no impedance matching, nothing. This port. This is okay. Let's say Z parameter if we plot, maybe magnitude if you see. So this is like some 2.5 kilo ohms something is there. Because why 2.5 kilo ohms it is there? This transistor we gave some on resistance. It will have we gave 2 micro. So maybe because of that it will have some on resistance. Because of that you got some Z profile. Maybe because of that you got some 2.5 kilo ohms on resistance. Along with that, this resistance effect will also be there. When you are doing simulations, just play around and check what is this resistance effect is there. What is this switch effect is there on the impedance and all. Okay, so these are the conversion gain, noise figure, and S parameter simulations. And another one we have wanted to see is linearity simulations, IIP3. For that one, we'll do QPSS and QPSC. Before doing that, we'll make certain changes. Let's say this one is instead of giving constant 1 volt, this PSC magnitude you give variable. Let's say the same like LNA only. This both variables I give Pin. That Pin is anyway here it is there, -40 something. I'll disable all this. In the analysis, select the QPSS. In the QPSS, it is showing all the tones, right? FLO and FRF. So shooting or harmonic balance, you can select the engine. Let's say This FLO is my large signal, FRF is moderate signal. I'm giving more tones, more harmonics, 5. So here frequency divide ratio for large tone. Since we are doing FRF and FLO are at equal, we are keeping 1. Maybe all your experiments, it will be the same. Certain cases, it will come when you are doing with harmonics, also you will use to down convert. Means your FRF is, I mean FLO is much lower, you used to down convert. That time you have to give the this frequency divide ratio of large tone. This large tone, what we are defined here, LO, that we will have to give here, but for your simulations keep it 1. Okay, and based on this harmonics, it will calculate here total harmonics. Let's say if I do 3, if I do keep 3, see the total harmonics are 49. If I give 5, it is changing to 77. So it will calculate. Now here we will do sweep. So select the variable. Let's say P, same like PSS PSC only. Instead of that, we'll do QPSS QPSC. Start, let's say minus 62 or minus 52. I'm doing, let's say plus 20. I wanted to sweep. Step size 1 I am taking. Apply and QPSC. Where you wanted to take the frequency, same single point. Let's say this is the 900 megahertz and this is I want to keep like 902 megahertz. I wanted to just do one calculation. So 903 megahertz. Here also I'll keep just 3 harmonics I'm taking here. Apply. But here what will happen? FLO is at 900 megahertz. FRF is at also 900 megahertz. And another tone we are giving at 903 megahertz. So here, since we are giving the one tone is at 900 megahertz, that will become to 0, means that is become DC. You will not see output 2 tones. Yes. So let's say we'll change this FRF to 902 megahertz. Then where these two will down convert, if 902 I give with respect to 900 LO, then it will be down converted to 2 megahertz. So here this 2 megahertz is my small tone. This FLO is a large tone, means the large tone means your LO. These two also large only, but large signal analysis only, but consider this is a moderate. Okay. So this 2 megahertz one with respect to LO, it will come to 2 megahertz. I mean 902 megahertz will come to 2 megahertz, and this 903 megahertz will come to, can it down convert, 3 megahertz it will come. So with these two, where the IM3 products will come. 902 and 903 gave, those are down converted to 2 and 3 megahertz, 2 megahertz and 3 megahertz. So where this IM3 products will come for these two?
1 and 4.
1 megahertz and 4 megahertz. Same. So do the simulation. There you have no down conversion in LNA. Here the down conversion takes place. That is the only difference. Since you are not dealing with any harmonics and all, these are straightforward analysis. Sorry, straightforward simulations, not analysis. Maybe some problems. These are may come because of when you are giving like 20 dBm signal, like you are sweeping from minus 60 to plus 20. That is large. Because of this, you will get this kind of messages, warnings. Direct plot, main form. If you don't forget to watch this log. Here sometimes it will come these many notices, this many warnings. So check what are those notices and what are those warnings, and understand what it is there. If it is really a problem or it is because of what, based on the input it is coming like that. So sometimes few can be ignored, few can't be ignored, few notices. So please check. Since we are giving here plus 20 dBm, this of course this will not handle. So those notices are coming, those warnings. So now go to the QPSC, IP and curves, same like, and net we are taking variable sweep. Let's say minus 30 dB. I wanted to extrapolate. So now here you need to select first order harmonic and third order harmonic. Now where is your first order harmonic is there? 3 megahertz, and that one is 1 and minus 1 megahertz one. So if you select these two and select net on the schematic, it is coming something kind of this profile. Maybe somewhere it's going wrong, I think. It is not extra, it's not following this red line, right? So where it's gone wrong? Sorry, 3 megahertz, 2 and 3 megahertz are first order harmonics, right?
Yes.
Megahertz, 3 megahertz. If you select wrong harmonics, it will come like this. This is your -1 to 0. And this is 1 comma -2. What is this 0 comma -1? It should extrapolate exactly to this. If it's not extrapolating, you need to go somewhat below and check. Okay, but the simulation procedure is same. But select these harmonics. What is the first order harmonic and third order harmonic where it is coming exactly? Okay. While selecting, please this select this properly. Mostly it will come extrapolating properly. If it's not coming, just go below frequency, below power input and check where there that is coming linear or not. Or you can do another way, HB and HBAC analysis. You can select HB. You can give number of tones, 2 tones. Fundamental frequency, this FLO, what's the name? FLO and FRF1. Or names you can select. It will come directly, you can select, no problem. Same sweep, select design variable. Instead of QPSS, QPSC, you can say you can do HB and HBAC analysis also. Same way for doing this. 0.903 megahertz. Okay. Maybe it's not properly following, but it should follow. So maybe from lower frequencies, if you do, maybe it may follow. Okay. So either you can do QPSS, QPSC, or HB, HBAC. Both you can do for IP3 check. Okay. P1 dB also you can get from the same. P1 dB point, compression point you can select and plot. Similar to the same LNE analysis. Just the difference is you need to do PSS and along with remaining simulations. Okay. For verifying this conversion gain noise and SP. That's it.